So today we're going to be talking a lot about discontinuities, particularly in rational functions. And when we're talking about discontinuities, things like asymptotes and holes, it's important for us to keep in mind the definition of domain in a function. So if you guys recall, the domain of a function is the set of all values that go into the function. So it's the set of all x values that you can plug in. Typically, domains can be used to limit a function. Very commonly in like applications of functions in real life, since there are limitations in real life of what can exist, that is where domains tend to appear. However, in our functions, there can be times when there are mathematical limitations on the domain, reasons where the function is limited in what can be plugged in based on mathematical reasons rather than any sort of physical constraints that we are placing on it ourselves. So today I'm going to start off with looking at what type of issues can arise when we're looking at domains of functions. So there's two main types of issues you can have with a domain of a function, and I like to refer to them as the domain problem children. So the first issue that you could have is division by zero. This is the focus of what we're talking about today, and it's very common in rational functions. Division by zero is what causes discontinuities such as holes and asymptotes. The other domain problem child is the square roots of negative numbers. That's what causes those imaginaries. This is an idea that we'll talk about another time. For now, we're going to focus on division by zero. So for example, say I have some rational function f of x, and that function has an x value or some sort of x related expression in its denominator. So like, let's say that I had x minus 2 in the denominator. And I can have whatever on top. Let's say, why not x plus 3? Sure. The thing is, in this function, if x equals 2, I plug it in and I get 2 plus 3 is 5 on top. 2 minus 2 is 0 on bottom. That's a division by 0. Now, last time we talked about why division by 0 is not allowed, right? So what happens is that because x equals 2 would give me division by 0, I would recognize that in my domain, x cannot actually equal 2. I should not plug 2 into this function, because if I plug in 2, I get an undefined value. So then what I would say is f of x has a domain of all real numbers, right? That r with the two lines means all real numbers, as in any number that's real, right? Not imaginary. And then I would say, but x cannot equal 2. All right. So now what we're going to do is I want to kind of quickly recap why is it that division by 0 is undefined. All right, so really quick, why does division by 0 cause issues? So for example, in the function f of x equals 1 over x, which is our classic rational function, why is it that when I have 0, it's 1 over 0 is undefined? So why is it that when I plug 0 in, it's undefined, right? So observing this function, when I plug x in with small numbers, division by a small number makes the fraction a larger number. Essentially, when I divide by 0.1, when I do 1 divide by 0.1, I get out 10. When I divide by 0.01, right, an even smaller number, I get out 100. When I divide by 0.0000001, right, 6 zeros, I get out 1 million, 1 with 6 zeros at the end, right? So you can see the pattern here. As x gets smaller and smaller, right, as x gets smaller and smaller, the function gets bigger and bigger. So you can see here's let's say that this is 1, right? Oh. Let's say this is the value of 1. Well, 1 divided by 1 is 1, right? So let's put that there. And then as I get closer and closer, so 0.1 is here and it's up to 10, right? 0.01 is even closer and it's up even higher, and so on. And so what's going to happen is this function is going to go up towards infinity, as it gets really close to 0 from the positive side, right? And as x goes to positive infinity, this is kind of a side note, but as x goes to positive infinity, it's going to go towards 0, right? Because when I'm dividing by a big number, it makes it smaller. Makes sense, I hope. But what about from the negative side? What about when I have -1? Well, when I do -1, when I do 1 divided by -1, that gives me out a negative number, -1, right? Okay, what about when I do -0.1? When I do -0.1, I get out -10, right? So you see it's become more negative, actually. When I plug in -0.01, I get out -100, so it gets more negative. You can see the pattern. When I plug in -0.00000001, I get out -1 million. And so then, therefore, as I approach 0 from the negative side, it's going towards -1 million, or negative infinity, right? So you can see that in this function, when I'm going towards x equals 0, on one side, from the positive side, I'm going up towards infinity. So the way we would write that is we say the limit as x goes towards 0 from the positives, the function of f of x will equal infinity. All right. But then on the negative side, as the limit as x goes to 0 from the negative side, the function will equal negative infinity, right? Because it's going down. So what happens? So then what we observe is like, okay, so what happens when I actually plug in 0? Well, I'm getting out both infinity and negative infinity. That's not possible. I can't get two values out from 1 divided 0. So therefore, it's undefined, right? So I know for sure this is undefined. And what we observe in the graph is that this up and down on either side is called a vertical asymptote. Okay, so you can see here this sort of dashed line that it's going up and down around. This is what we call a vertical asymptote. So essentially, having a factor in your denominator, right? Having something in the denominator that causes division by 0 will create vertical asymptotes, right? Now, you may now be thinking, okay, but Mr. Hobaugh, previously we observed that you could also have, instead of a vertical asymptote, a hole in the graph, just a hole, where the line looks mostly normal. It looks normal except for some small hole. So let's look at what can cause a hole in the function. So to begin our discussion of holes in functions, I want us to take a look at this function r of x. R of x equals x squared plus 5x plus 6 over x plus 3. In this function, based on what we've been talking about, we can tell that there should be some discontinuity at x equals -3, right? And you can see from this table of values that I've created that at -3, the function is undefined, as we would expect. That is great. That is great. Now, what I want to do is have us take a look at the rest of the values in this table. And what we're going to do is we are going to plot to the best of our ability, the best of my ability. We're going to plot these points and take a look at what this graph looks like. So when x is equal to -2, if I plug that into this function, I should get out 0. So I would have a coordinate at -2, 0. What else do we have? When x is -2.9, right? Essentially, I'm plugging in x values that get close to -3, but aren't quite -3. Just like we did when we were plugging in values getting close to 0 for our 1 over x function. So when I plug in -2.9, I get -0.9. So -2.9, which is pretty close to -3, I get -0.9. So that'd be around here. When I plug in -2.99, I get -0.99. So you can see that's pretty that's essentially so close to this point that it's not really worth my time even trying to distinction it. At -3, it's undefined, so I will not include any coordinate at -3. At -3.01, it has a y value of -1.01. So that's extremely close to -3, but not quite. It's extremely close to -1, but not quite. So there's a coordinate right about here, right? Negative 3.1, it's negative 1.1, pretty much same as that. And at negative 4, its y value is negative 2. Now, what you can observe here is that if I connect this line, what's happening with this function is it is a line going in this diagonal direction. There's a line going this way in this diagonal direction. And in fact, if you were to continue to plot this, you would see it go in that fashion if you were to continue to plug in points. And there is no value here at negative 3. So what I like to do, and what we will do in our class, is draw a little hole there. This hole here represents the fact that there is no value at negative 3. So I'm going to label that as negative 3, comma, negative 3, comma, undefined. All right, so what we see here, y'all, is that instead of creating an asymptote, right, where the function is going up on one side and down on the other side, this function here, r of x, has a hole in its graph. And that hole essentially is just a single coordinate that's missing. As close as I can get to negative 3, it will still have value in this line until I'm literally at the coordinate of negative 3. So now what I want to do is take a look at this function and talk about why is it that that there was a hole here instead of an asymptote when we knew that there was a discontinuity at negative 3. Now, the secret to why there's a hole in this function lies in us looking at the equation of it a little bit deeper. To begin with, it'll be useful for us to think about the zeros of the numerator, right? The factors of the top of the fraction. So what I'm going to do is I'm going to factor that. X squared plus 5x plus 6 will factor to x plus 3 times x plus 2. In the denominator, I still have my x plus 3. So what we can observe here, y'all, is that there was an x-intercept at negative 2, and that's from the x plus 2 value, factor here. But there's also a factor of x plus 3 here, and I have no x-intercept there. Now, the reason for that is because there was a factor of x plus 3 on the denominator as well. So what we can observe is in this function r of x, when I plug negative 3 in, I should be getting out 0 on top and 0 on bottom. Now, 0 divided by 0 is actually still going to be undefined because it's still a division by 0. It's still undefined. However, what we can observe here, y'all, is that the factor of x plus 3 on the top of this function and the factor of x plus 3 on the bottom of this function are essentially canceling each other out. And what's happening is that as a result, this function is equal to x plus 2. And what you can actually see is that the function of x plus 2 would have the exact same coordinates as this function has had. At negative 2, when I plug in negative 2, I would get out 0. When I plug in negative 4, I would get out negative 2 here. The only difference is that at negative 3, my original function r of x was undefined. And that's because even though when I simplify this function, the numerator and the denominator have a factor cancel out, I cannot actually forget where I came from. I still need to keep in mind what my domain of this function is. This function has a domain of all real numbers. Of all real numbers with x not equaling 3. So even though I've simplified it to x plus 2, I still need to keep in mind that my domain is all real numbers without negative 3. Oh, I should say x does not equal negative 3. Okay, so to sum up what we're seeing here, y'all, because of the common factor in the numerator and the denominator, the effect of it, right? The effect that would normally create, the effect that a denominator having a 0 would create, that effect of an asymptote, has been canceled out, right? So instead of creating the crazy asymptote, it actually will look exactly like the x plus 2 function, just with a little hole in it. All right, so to sum things up about discontinuities, we have two types of discontinuities. We have vertical asymptotes and we have holes. So first of all, division by 0 is what causes these discontinuities in our functions. So if there is a factor that can equal 0 and that factor is in the denominator, then that creates these discontinuities. Vertical asymptotes are caused by what we call a non-removable discontinuity. This means that there's some factor in the denominator which can equal 0, right? But that factor is not able to be canceled out. So for example, in f of x equals 2x plus 1 over x minus 3, there is this x minus 3 factor in the denominator, which could equal 0 at x equals 3. And it would not actually be canceled out by the numerator. So therefore, we have a vertical asymptote at x equals 3 for this function. On the other hand, holes are caused by what we call a removable discontinuity. This means that there's a common factor in the numerator and the denominator, and that factor is able to be equal to 0, right? So for example, if you see in my example function here, g of x, I have 2x squared minus 5x minus 3 over x minus 3. If I factor that numerator there, I would see that there's a common x minus 3 factor, which could cancel out. So I'm going to go ahead and cancel that out right quick. And so because that denominator is able to cancel out, I would actually say that that's a removable discontinuity because it cancels. And that creates a hole at x equals 3. And why does that happen? The possible 0 in the denominator means that there is a discontinuity, right, which affects the domain. So essentially, from the beginning, this function has a restricted domain. It has a restricted domain from that x minus 3 in the bottom, such that the domain is all real numbers, but x cannot equal 3. And then, however, there's a common factor in the numerator, right, that x minus 3 on the top, which means that there's no impact on the overall shape, right? So it doesn't create an asymptote. So this is kind of the sum up of asymptotes, specifically vertical asymptotes and holes. The next thing that we're going to finally talk about, and that this is going to conclude our lesson today, is end behavior of these functions. We previously talked about end behavior with polynomials, and we're going to start off with a little recap of that and then see how that translates to rational functions. So when we're looking at end behavior, previously we identified that in a polynomial, the end behavior is completely determined by the leading term, the term that has the greatest power. As a quick recap of why that happens, I just want to direct your attention to this table. So here is a table of x values compared to them plugged into this function p of x. So if I plug in large x values, like say 100, I plug in 100, and when I plug it in, I get minus 30,000, negative 30,000, plus 400, minus 2. And summing that up, I would get negative 29,602. So you can see that the 400 from the 4x has kind of changed 3x squared a little bit, but not by too much, right? It's kind of like this 4x term has affected it a little bit. Negative 2 basically has no impact, right? What's 2 in the context of, tens of thousands? Then if we up the ante and we starting to look at x values that are even bigger, like 1,000, you see that I get negative 3 million, and this is gonna only be 4,000, right? This is purely because of the power. This is because the exponent is bigger. Because I have a greater power affecting the x, then it just grows so greatly, right? In fact, you can see as I plug in a million, when I plug in x is a million, negative 3x squared would be actually negative 3 trillion. Negative 3 trillion. That is 12 zeros there. And then 4x is only going to be 4 million. Now you may be saying, 4 million, man, I wish I had $4 million. That's a lot. But in the context of 3 trillion, 4 million's kind of nothing. In fact, I may as well claim that P of X is still equal to negative 3 trillion at the end of the day, even though I've got these guys here. So what that means is when I'm looking at end behavior, as in the looking at what happens to this function as x goes towards infinity, I would recognize that this function is going to entirely be dependent on its leading term. And the leading term is negative and it's squared. Well, infinity being squared is still infinity. And but then it's getting multiplied by a negative. So that ends up being negative infinity, right? Because it's a positive times a negative is still negative, even if it is infinity that we're looking at. So in terms of the end behavior of this polynomial, we saw that as x gets big, the function goes to negative infinity. And the same would happen with as x goes towards negative infinity. Negative infinity squared would be positive because a negative times a negative is positive. Then it gets multiplied by another negative, so this function would go to negative infinity. We've already seen and talked about end behavior a lot before in polynomials. Now let's see what happens when we look at a rational function. Now, rational functions, if you recall, are just polynomials dividing each other, right? So if I want to focus on the end behavior of this rational function, if I'm trying to focus on the end behavior of this rational function, all I truly care about are the leading terms. And that's going to be the leading terms of the numerator and the leading term of the denominator, negative 3x squared and x squared. So what I'm going to do is I'm going to actually put that as my what I'm plugging into, just because at the end of the day, 4x minus 2 and minus 4 here are all going to not really matter too much when we start plugging in large numbers of x. So let's look at what happens when I plug in these x values to this leading term situation here, right? 100 plugged in would be, well, negative 3 times 100 squared is negative 30,000. But then it'd be divided by 100 squared, which is 10,000. What does that end up equaling? That equals negative 3. How about when I plug in 1,000? 1,000 squared is 1 million times negative 3 is negative 3 million. And 1,000 squared on the denominator is 1 million. Well, negative 3 million divided by 1 million is negative 3. Oh, that's crazy. What about, it couldn't possibly be the same for 1 million, could it? 1 million squared is 1 billion times negative 3 is negative 3, or I mean trillion, negative 3 trillion. It's so tiny to write. And that'd be all over 1 million squared, which is 1 trillion. Well, what's negative 3 trillion divided by 1 trillion? Negative 3. So what we see is the end behavior of this function is actually equivalent to it's equivalent to if I take the leading terms, negative 3x squared over x squared, and I actually can simplify it. Well, x squared cancels out with x squared, and I'm left with negative 3. And what will happen is that this function here, r of x, will have an end behavior of negative 3. What does that look like? Well, end behavior is discussing the value of the function itself, right? The y values. So here is, let's say that this is negative 3. This function is going to have, it's going to do all its crazy asymptote stuff in the middle and all that. But at the end of the day, let's say it has an asymptote here and here. Let's just say it has that, right? But at the end of the day, its end behavior is going to go towards negative 3. So what's going to happen is this function is going to, I'm a real, I don't know exactly what this function is going to look like in the middle. I would need to solve that. But like, let's say it does something crazy like this. It makes an asymptote on either end here. And then over here, it comes down from the bottom. And as it goes towards negative infinity, it should go to y equals negative 3. And same thing on the other side. As it goes to positive infinity, it should go to y equals negative 3. So you can see that the end behavior of it, right? The behavior as x goes to infinity and negative infinity is going towards y equals negative 3. So that's that's a little bit of an intro to what we can expect end behavior of functions to look like. So what I'd like y'all to do is go ahead and, now that you've checked out this video, you've learned about holes and vertical asymptotes, and now you've kind of started to see a little bit about end behavior. I would like you guys to go to the next portion of this homework, which is the actual homework assignment. And in that assignment, you will practice still solving for X-intercepts and Y-intercepts, and you will start identifying holes and vertical asymptotes. And we'll also start looking at end behavior of functions. If you don't feel like you have a super solid basis of how to actually graph these rational functions, that is perfectly reasonable. I don't expect y'all to be able to graph these perfectly just yet. But you can see that we're starting to be able to form an understanding of how to graph them, right? So for example, if I had this rational function here, r of x is equal to 2x plus 1 over x minus 3, I can identify all of the various features of this rational function, such as the x-intercept, the y-intercept, any discontinuities, and the end behavior. Oops. In a rational function, these 4 pieces of information are going to be the most essential things to find. So how do we find x-intercept? Remember, it's the zeros of the numerator, right? Because it's when it's the x-intercept is when the function equals 0, but this can only equal 0 if the top is 0. How do I find y-intercept? I plug in 0. It's when x equals 0. Remember, that's just like our normal functions. Discontinuities are the zeros of the denominator, of the bottom. And we've discussed already how to identify whether the discontinuity is a vertical asymptote or a hole. And finally, the end behavior is the leading terms divided. So let me separate these things so that it's a little bit easier to see. So let's use this to solve for all the features of r of x here. Oops, a little lag there. The x-intercept would be when this equals 0. That'd be at x equals -1/2. The y-intercept would be when I plug 0 in for x, which would give me 1 over -3. That's -1/3. The discontinuity would be the zeros of the denominator. That is discontinuity. That's at x equals 3. And I should identify that this is a vertical asymptote because there is no x minus 3 factor in the numerator. And then finally, I could determine the end behavior of it. The end behavior, I'm going to call that EB, would be the leading terms divided. 2x divided by x, which would be 2. So now I've identified all these features. I actually could just go ahead and graph it. I'm just going to sketch the graph real quickly. X-intercept at -1/2. This looks like it could be -1/2. Y-intercept at -1/3. Here is -1/3. Discontinuity of a vertical asymptote at 3. Here's 3. So I'm going to do my dashed line vertically. And the end behavior is 2. Well, here's 2 on the y-axis. And it's going to make my end behavior is actually oftentimes, if it's horizontal like this is called a horizontal asymptote. And so then what does it look like? Well, I can know that from these 2 points, my line is going to connect here. And from this vertical asymptote, I know that it's going to go down towards -infinity. going this way, I know that from this horizontal, the end behavior, that is going to go towards y equals 2. And then based on what I know of this asymptote, I know that if it's going down here, and I know that it's actually got to be coming up from here, and this is where I know that your guys' knowledge of graphing rational functions is not yet too solid, but I know it's going to come from above, because if it came from below, I would need to cross the x-axis again, wouldn't I? If I came from down here, I would have to cross the x-axis to get to that end behavior. But there's no x-intercept there, is there? So I know that it actually comes from up above and goes off towards y equals 2. And this is my sketch of the graph of r of x. Cool. So now that you guys know about discontinuities such as holes and asymptotes, and you know about end behavior, we actually will begin to start attempting to sketch these graphs of rational functions a bit.